Hello there, and then welcome to a brand new video. In this lesson, we are looking at application of vectors in geometry, and specifically, we are looking at how to apply it in what triangles. By the end of this lesson, you should be able to represent the sides of a triangle using vectors, and also apply addition, multiplication, finding midpoint, and even dot product in relation to triangles. Without much ado, let's quickly look into it. Now, we would first of all need to recap what we need to know before we can go into the lesson. First of all, we have said that vector is a quantity that has both magnitude and direction. You see, it has both magnitude and direction. We have said that if you have a point, so let's say you have point A, which has coordinate x1 and then what, y1. Then if you have B, which also has coordinates x2, y2, then it means that a vector that links A to B, written as A, B, is then equal to the coordinate of B, that is x2, minus that of 1, x1. You see? And then for the y component of AB, it is going to be what? Y2 minus y1. It is important you take note of this. We also said that to find the magnitude of a vector, that is for AB, or let's just take vector A. So for vector A, if you want its magnitude written as this, then it is simply the square of its component. So each component in this case is x1, we square it, and then that of y1 as well, we square. And then we find the square root of this sum, you see. And then we finally spoke of the dot product. That is, if you have A here and then B here, and what's their dot product? That is A dot B. We said it is the product of their components. That is x1 times x2, then plus y1 times what? Your y2. So this was what this is what we've done so far in relation to what? Vectors that we will need to what? Apply in what? Triangles. So without much ado, let's quickly look into it. Okay, so starting off with this here, it says the vertices of a triangle ABC are 2, 1, 6, 4, and then C, which is 3, 6. You have to find the vectors representing the sides AB, AC, and then BC. Now, as I always do, let's go to the graph sheet and then plot them out. If you don't have, you can just follow as I do the plotting. So A was 2, 1. So we come to X being 2, then we go up to Y is 1. Now our next one is B, whose coordinate is 6, 4. So we come to 6 and then we move up to 4. All right. So let's quickly do that. 6 and then 4. This is the point over here. And then we come to our last coordinate, which is C, with coordinates 3, 6. So X is 3, then move up to 6. Okay. So since it is a triangle, we are not to be told to complete the sides. Hence, we need to join the points together. So joining the points together, I'll join this point to this here, this to here, and then this also to here. Now you don't forget to write out the coordinates. So remember, this side here was our A, which was 2, 1. So A, 2, 1. Then this, which is the 6, 4, was our B. So B, 6, 4. And then the C, which was 3, 6. So 3, 6. Now back to the question. We have to solve for AB. AB. So for AB, we know AB from our lesson so far is the position vector of B minus that of A. You see? So substituting So our B then is substituted, which is 6, 4, then minus the A. The A was what? 2, 1. So evaluating, we have 6 minus 2, and then 4 minus 1. That is x component to x component, then y component also to y component. 6 minus 2 gives us a 4, and then a 4 minus 1 gives us a 3. So this here is our vector AB, and that is it. So we use this same method to solve for the rest. All right. Okay, so evaluating the second part, which is AC, we have C minus A. You see, that is the second one minus the first one. So our C, which was 3, 6. So 3, 6 minus A, which was 2, 1. And simplifying this, we have 3 minus 2, then 6 minus 1. And you know 3 minus 2 will give us a 1. So we have 1, then 6 minus 1 then gives us a 5. So our answer for AC is 1, 5. Then the last one, which is actually BC. Now that also gives us what we have here, BC, which is C minus B, right? So if you have been following all that we've been doing so far, then you can write the answer down in the comment section. Well, if you're able to solve it, then you should be expecting an answer of -3, 2, right? And that is all. So with this, we have been able to determine the vectors of the what? Of the triangle, right? And we had A, B, B, C, and then that of A, C. Now let's look at the next question. Now the next question says, using the vectors we have found in our previous example, or that is this triangle over here, then we have to calculate the length of each side of the triangle. So we want the length of this side, we want the length of this side, and we also want the length of this side. How do we go about this? Let's start with what? AB. Now, for AB, we're able to find its vector to be what? 4, 3. And remember, the length or the magnitude of a vector is given as the square root of the sum of the squares of its component. Hence, the magnitude of AB, that is written as this. You see, we have these two lines here. Is equal to the square root. So first of all, we square the component. So 4 squared plus 3 squared, and then we find its square root. 4 squared gives us a 16 plus our 3 squared, which is 9. You see, so evaluating this, we have the square root of 25. And you know the square root of 25 then gives us what? 5. So 5 units. That is, the magnitude of AB is 5 units. Meaning, if you have to measure this from A to B, you are getting what? 5 units. Now, let's see how that true is when we take a ruler. So, provided your scales are perfect, okay? Because as you can see here, I have said my scale is 1 centimeter is 2 units, okay? So, provided you had an accurate scale, then you can even measure to confirm your calculation. So let's measure and see. I have my 0 here, and then aligning my ruler on my graph, and I'm going to get something like this, 0 being here, and the B is exactly on my 5 centimeter mark. You see, so 0, 1, 2, 3, 4, and then 5. You see, so even graphical method confirms what you do per your calculations. Let's continue and see what we are going to get for the rest. Now, for AC, we already solved for its vector, and that was 1, 5. You see, So using the same method to solve for its magnitude, we say the magnitude of vector AC is then given as 1 squared plus 5 squared. And evaluating further, we are then going to get the square root of 1 squared gives us 1. So 1 plus 5 squared is 25. So you now have 1 plus 25, which is the square root of 26. If you are not using calculator, you can just write it as root 26 units. But if you have the calculator and you have to simplify further, you are going to get 5.1 units. And this is the magnitude of what? A to C. Now, we have to solve also for the magnitude of B, C. If you have been following what we've been doing so far, then I do expect you to pause and then try that on your own. Now, if you're able to do it on your own, then you should be expecting an answer of 3.6 units. But in said form, it is the square root of 13 units. All right. So you see, we've been able to apply the magnitude method to find the magnitude of this triangle over here. There is one last concept we can also apply in triangles, and that is the dot product. So let's look at this question here. Now, if you have to determine if triangle ABC is a right angle, we know what a right angle triangle is. It's a triangle where we can say one of the angles is actually a 90-degree. So with what we've done over here, there is a 90-degree over here. Now, per our drawing here, none of these angles looks like a 90-degree, you see. So graphically, we can just go directly and say that no, this triangle isn't a right angle one. By using a dot product, we know that the dot product of two vectors equals 0 if they are perpendicular. So with this now, we want to determine if the dot product of this one and this is 0, or this and this is 0, or this and then this as well is 0. You see? So with that, let's quickly write the vectors we solve for. Let me just go back and look at them and come and write them here. So here are the points. AB was 4, 3, AC was 1, 5, and then BC was -3, 2. Now, we first of all want to solve for AB dot AC. You see, and we have said that if you get 0, then it simply means they are perpendicular. Hence, there's a right angle. So substituting, we have 4, 3 dot AC, which is 1, 5. Evaluating further, it means you have 4 times 1, which is 4. Then plus the 3 times 5, which would give us what? A 15. Simplifying, we have 19. And this 19 here is a positive number. Now we said if the dot product is positive, it actually means there is an acute angle. There is what? An acute angle. And as you can see, vector AB, this is AB and then this is AC. The angle here is actually acute. It confirms that the angle here is not 90, but an acute one. Let's look at the next one. So since we've done for AB, AC, let's look at AB dot BC. So just as we did, it is then going to be our AB, which is 4, 3 dot BC, which is -3, 2. We have 4 times -3, which is -12, plus your 3 times 2, which is 6. Adding this then gives you what? -6. That is 12, -12 plus 6. So we have A, B dot BC being equal to what? -6. Now, you remember we said for vectors whose dot products are negative, that it means the angle between them is what? An obtuse angle. It is an obtuse angle. Now, if you look at AB, so this AB and then BC over here, we have two angles that we can identify. So this angle here, which is the interior angle here, you see, and then this one over here, which is the exterior. So this property is trying to tell us that the exterior angle here is what is an obtuse angle. You get it? So don't be confused why it is negative, trying to refer to the interior angle, but rather it is referring to this one here. In view of that, let's look at the last one, which is BC then times, so your BC, this here, dot your, so BC dot AC. Now, per what we've done so far, even if you don't really, or you've not gone through the dot product lesson, per this example, you should be able to what? Solve for dot product by now. Now, if our BC is -3, 2, and we want its dot product of AC, and AC is 1, 5. You can pause at this moment and then try and then evaluate that. Now, if you're able to evaluate it, then well done. Hence, you are going to get a -3 plus a 10, which is a 7, right? So you realize that all of this dot product didn't give us 0. None of them give us 0, which means that none of the lines are perpendicular to the other, right? Hence, that completes what we are doing here. So this and many other are the applications of vectors on triangles, right? But with respect to time, we can't do enough. But I'll give an exercise you can try on own just to test your understanding based on what we've done so far. So here are the questions. There are just 3 of them, just as similar to the ones we have solved. You have points on a triangle, and for this one, you have to calculate the length of the 3 sides. For the second one, you have to apply the dot product to check if the angles are right angles. Maybe if one of them is. Then for this here, you have to determine which angle is the right angle. So you would be applying the magnitude of a vector and then the dot product as well. This has been a very long lesson and I would like to end here. This is How Beyond Numbers. And if this is your first time visiting this channel, you can always choose to subscribe if you so do wish, so that anytime I release a lesson, you'll be notified as well. If there's any issue of concern, as usual, you can always let me know at the comment section. Bye for now, and then see you in our next session where we look at applying vectors toward parallelograms. Bye for now.